go over centripetal force and centripetal acceleration, I just want to remind you that tomorrow is our physics competition, and I wish everybody good luck, and I hope everybody gonna win, and everybody would be able to take Einstein home. I have so many Einsteins here in the classroom waiting for you to take Einstein home, but you have to win 3 times to take the Einstein home. Good luck for tomorrow. That out of the way, let's start our conversation with centripetal force and centripetal accelerator. What is centripetal force? When a body, right? When a body experiences force to the center, the body, the force that keeps the body in a circular path, right? Centripetal force is a force that keeps a body in a circular path. That's the centripetal force. Now, see this object, a bucket, and this object also a bucket. So in this case, the bucket will follow a circular path because bucket is attached with a rope, right? So there is a net force over here, and there is a net force over here. Of course, net force would be due to gravity, right? And this case, what happened? There would be no centripetal force because it is in free fall. So the force would be the force of gravity. And although there is a net force, there would be no centripetal force over here because it is not making a circle, right? On the other hand, this is circular. This object, the same bucket is forced to create a circle because there is a centripetal force coming from the rope. Why we are using this? We are modeling moon and earth. There is no rope between moon and earth. What is it? Gravity. So this rope is gravity, right? So which is centripetal force. You can call this rope or you can call it centripetal force, right? We're going to call it net force or centripetal force. Centripetal force, okay? We're also going to call it rope, right? Because it is rope. When you talk about bucket, you grabbing the bucket, you grabbing the rope which is attached to bucket, and the water inside the bucket would be the moon, and the rope is, of course, the acceleration due to gravity. And if you cut the rope, what happened? If you cut the rope, the bucket will fly at the direction of what? The velocity, okay? The direction, there is a velocity that keeps it not falling. So the centripetal force keeps it falling, and there is a velocity that keeps not falling. So the relationship between the centripetal force's velocity is perpendicular, right? So we're going to start our conversation with that. So let's create 3 loop, 1, 2, 3, all right, and every loop has a center, right? So this is a centripetal force, this is a centripetal force, and there is a center, right? Okay, good. Now, if that is a rope at time t1, right? At time t2, there must be another rope because the bucket would be here. Time t2 bucket would be right here. This the same bucket. This is the same bucket is going to be right here, right? Because at time 2, this is time at time 1, at time 2, it is the loop. So at time 2, the bucket going to be right there, right? So the rope, the size of the rope doesn't change. The same rope, it is the same rope. So you're going to put the rope, and this is the same rope. You're going to put the rope over here, right? The size of the rope doesn't change. You have it's still the same rope, but this is not toward the center, right? However, if you do videotape it in slow motion, you'll see that the rope really changes the angle as you rotate it around your hand. This is not impossible to do. I'm not asking you to go to the moon. I'm asking you to rotate a bucket. Fill the bucket with the water and rotate it around your hand, around your hand, just like this, so that it makes a circle. So what happened? It doesn't changes the size, but it changes the direction. Why it changes the direction? Because the centripetal force is acceleration is at the direction of the center. Okay, so it is always toward the rope is always toward the center. Okay, so how can we make that happen? So let's put the bucket over here. Instead of bucket, we're going to just put a dot. So let's let's put, there is a velocity over here, right? Velocity keeps it, velocity keeps it not falling, right? Velocity keeps it not falling. So we're going to call rope 1, right? Rope 1. And this is, we're going to use the different color. Let's use the green and the velocity. This is velocity, right? Velocity 1. And rope 2, this is rope 2, but again, rope gonna be changing the direction, so rope gonna look like this. So this is rope 2, and this is of course velocity 2, velocity 2, right? And this is delta L. What is delta L? The arc of the circle, that's delta L, because it's gonna some amount of time, it's going to take some amount of time to create one, to make one revolution or one cycle. When it make one cycle, that is 2 pi r, but it is not 2 pi r yet. It is just delta L, a section of the circle. Okay, good. If this is the case, then we can put the velocity over here. So this is the velocity, right? So I'm going to put that over here. I'm going to put that over here, right? And then I'm going to put the few seconds later, it is over here, right? So I'm going to put that over here. So put that over here, but hey, again, it never changes the size, but it changes the direction. So I'm going to change in the direction. Excellent. This is like perfect. Perfect. Okay, it's changing the direction to the center. Okay, good. All right, so now what happened? The velocity. This is the velocity. Okay, so this is the velocity. Is this perpendicular? Yes, this is perpendicular. This is the velocity. So this velocity right here, it does not, velocity doesn't change at the same size. But look, this is not perpendicular. This is perpendicular. But this is not perpendicular. Okay, what happened? Well, the velocity has to be perpendicular. Why? Why is that? Because the velocity is always at the direction of the is always perpendicular with respect to the with respect to the x with respect to the centripetal centripetal force. So make it perpendicular. Okay, let me see. It is perpendicular. Okay, let's make it purple. Let's make it purple. This is kind of perpendicular, and let's make it blue. Make it blue. All right. So let's put it over here. Okay, put it over here, and put one over here. Right. Put one over here. Oh my God! What is happening? The change of velocity. The change in velocity is this one. So this is velocity 1. This is velocity 1. This is velocity 2. So this is velocity 1. This is velocity 2. Which one is velocity 1? That is velocity 1. This is velocity 2. This is velocity 2. And this is the change in velocity. This is the change in velocity at the direction of the centripetal force. Oh my God. So there is an angle, right? There is an angle, right? And these are the same angle we are talking about. Okay? So if I put A over here, B over here, and C over here, then what happened? The V1 is perpendicular. So BA is perpendicular to V1, and CA is perpendicular to V2. If this is the case, then ABC is similar to V1, V2, and of course the delta V, right? So ABC can be replaced of R1, R2, and delta L is similar to V1, V2, and delta V. So this is these are the similar triangle which you can make, of course. So now I'm gonna just do that. I'm gonna bring them over here, bring this one over here, and I'm gonna call this one theta, of course, and I'm gonna call this one V1, this one V2, and this one delta V. Is that right? Now, of course, I'm going to bring the other one. I'm going to call this one L1, this one L2, and this one L, right? Okay, now, now these are the similar triangle. Now, notice V1 is equal to V2. So we can call it V. Why? Why is that? Because, look, the velocity really never, the size of the velocity never changes. So if the size of the velocity never changes, we call it constant velocity, right? No, we don't in this case, right? If the velocity never changes, we call it constant velocity when it is at the straight line. But in this case, we don't call constant velocity. Why is that? Because, hey, change in velocity causes the acceleration, right? By definition, acceleration is change in velocity over change in time. So where do you see the change in time? Hey, t1, t2. And where do you change the change in velocity? The change in velocity is right here because it changes the, it's not a straight line because it's carved. So there are two ways you can have acceleration. One is by increasing the velocity. So this is acceleration. This is an example of acceleration. This is also an example of acceleration. Okay, velocity 1, velocity 2, velocity 1, velocity 2. This is an example of acceleration. So there is acceleration is not 0. Acceleration is not 0. And here acceleration is not 0 as well. So you have a velocity 1. And if you have the same vector over here, okay, I'm sorry, let's do it again. If you have the same vector over here, then this is, of course, change in velocity, because this vector not going to look like this. This vector going to look like exactly how it should look like. It should look like 90 degree, it should look like perpendicular with respect to what? Centripetal force, just like this one, right? Okay, so there is a change. There is a change in what? So if you put this together, if you put this velocity with this velocity, then you have the change in velocity. So change in velocity over change in time. How change in time? Because this is t1, this is t2. So change in velocity over change in time is by definition acceleration. So three ways you can find the acceleration. This is acceleration, and this is also an acceleration. Okay, now good. So far so good. Now let's use the similar triangle property to prove the centripetal acceleration that we wanted to prove. So what are you going to do? You're going to write v, delta v. You're going to write L, delta L. Again, just like the velocity, the L1 is equal to L2 is equal to L. Why is that? Because, hey, you have a bucket and you have a rope. Just because you're rotating it, the rope doesn't become smaller or bigger. Which rope is bigger? The red rope or the green rope? Oh, both rope of the same size. Okay, get that. Delta V over delta L is equal to V over L, right? Okay, so cross multiplication, delta V L is equal to V delta L. Now, the time is behind the scene. Why the time is behind the scene? Because, hey, there is a time difference between even B and even C, right? And that time is not 0. It's very close to 0, but it's not 0. Okay, so the time is behind the scene, so maybe we want to divide it by time. So then if you divide by time, as we've been saying, delta V over delta T is acceleration. What type of acceleration is it? Center seeking acceleration, right? So you put C. And then there is a M. Hey, you already probably see what you are looking for, right? Um, so this is L over T. L over T is V, right? Velocity is distance over time. D as a unit is meter, and L as a unit is meter, because L is the length. So they all are the same. So velocity is now, this one is also velocity. This velocity and this velocity, okay? So now what do you have? You have acceleration. You have acceleration, L is equal to V square. V times V is V square. So centripetal acceleration is V square over L. So what is the difference between L and R? Because there is no difference. The SI unit for L is meter, SI unit for R is meter. So it is convention to use R. So centripetal acceleration is V squared over R. All right, good. Now we know the centripetal acceleration. What is centripetal force? Centripetal force is, of course, Newton's second law, F equal ma. Centripetal force means you put acceleration. Now you just want to, what you do? You just want to copy and paste it. So you're going to take it and you're going to put it over there. So M F force. So centripetal force is mv squared over r. We proved that. The roller coaster problem, problem number 1. So there is a roller coaster over here, right, on the top. So we are trying to find on the this roller coaster will three things. Number 1 is you will experience heavier. Number 2, lighter, or Mr. Bari. Okay, or Mr. Bari will die. All right, Mr. Bari will experience heavier, lighter, or will he die? Okay, so what is given? The mass is given 1000 kilogram. What else is given? The radius is given 10 meter. What else is given? Velocity is given also 6 meter per second. We want to see whether Mr. Bari will survive with when he elevator the roller coaster goes to the top. So first thing we need to know, what is the required velocity for this one to survive, for this one not to fall, because it is falling. How it is falling? This is Fg and this is Fn, right? So centripetal force, there are two centripetal force, Fg and Fn to the center. So it is falling. So what should keep this one not falling? Velocity, right? The velocity, how big the velocity has to be so it doesn't fall. That's what we're going to find. Okay, so we always start our conversation with Newton's second law. So F equal to ma. We're going to make a small correction because everything is falling to the center, and that means south. That means negative. That means we are talking about centripetal force. That means we are talking about centripetal acceleration. Now Newton's second law looks good. We want to put all the forces we see at the y direction, because this is y direction. We see Fg, we see Fn, and we see minus m acceleration, centripetal acceleration is 0 square over r. Now we have to make a small correction by convention. Anything falling toward the south or down, we call it negative. So this is negative, this is negative. So this one is, we're going to bring this one over here. So mv square over r is minus, this one is minus mg is equal to fn, right? Okay, so fn has to be 0, right? Because you cannot have fn that is less than the minimum. Fn is 0. When something is falling, is in free fall, the fn is 0. So by setting fn is 0, we're going to give you the minimum velocity you need to survive on the top, because fn 0 means this one losing contact. Now fn is 0. Now fn is not 0 because it's not losing the contact. When it's losing the contact with the track, then fn is 0. Now fn is not 0. Now fn is 0. Okay, good. So far so good. Now factor out m. So v square over r minus z is equal to 0. So v square over r minus z is equal to 0. So v square over r is equal to z. So then you have v squared is equal to rg. So v is equal to square root of rg. All right. So in this case, v has to be what? R is 10 and g is 10. So v is square root of 100. That means v is 10 meter per second. So minimum 10 meter per second for you to survive, right? For this elevator with this radius However, the velocity is 6, so Mr. Bari will not survive because 6 is less than 10, way less than 10. However, we want to prove it. We know he will not survive, but let's see why he won't survive. If his normal force is less than 0, well, then he won't survive. That's it. Well, now let's see whether the normal force is less than 0. So what is the normal force? Normal force, we already proved that when it is on the top, then it is m v square over r minus g. So Fn is m is 1000, v square is 36, this is 10 minus 10. So Fn is, you have 1000, you have 10, 36 minus 100. So you have Fn is 1000. We already see what is happening, 64 over 10, but be careful. So 0, 0 cancel, so we see that negative 6400 Newton. So yeah, our hypothesis was right. We said that he won't survive with 6 meters per second because the required velocity is 10 meters per second. And that is true. Again, we show that the normal force is less than 0, or at least 0, less than 0, so he won't survive. So we show it 2 ways that he won't survive. Now, if that is the case, now we're going to find out, we're going to change a little bit to see whether he will survive this time. So the roller coaster again on the same place, right? On the same place. Now it is at the contact with the track. It is at the contact with, no, I'm not gonna do that. So it is now at the contact with the track, probably because the normal force is more than 0, but we don't know. So let's say velocity. Let's change the velocity. 15 meters per second, and the radius is 6. Keep the radius same, mass, keep the mass same. All right. Now see, let's see whether he feel heavier, lighter, or he die. Okay, so again, Fn is in the top, so you're probably going to use the same formula, and that is v squared over r minus g. So Fn is, of course, 1000, and then v squared is then 225 over 10 minus 10, right? So Fn is, you have 1000, and then you have 10, you have 225 minus 100, all right? So then Fn is, then you have 1000, and this is 125 over 10, 0, 0 cancel. So Fn is, of course, 12500 Newton. So you have 12,500 Newton. Your weight is, of course, 10,000 Newton, right? So 12,000 Newton, your Fn is bigger than Fg, so you feel heavier, right? When Fn is bigger than Fg, you feel heavier. But hey, this is the sensation you're looking for. Otherwise, you won't be riding the roller coaster. Okay, this is not too much heavier. It's heavy. It's heavy enough for you to enjoy the ride. Okay, good. Question number 3. I'm going to be changing the velocity again. This time I'm going to probably change the velocity and change something else. Change the radius as well. So velocity, probably I'm going to keep the same velocity. I don't know, meter per second, but radius I'm going to change it. Radius, let's say 20 meter, and then I'm going to change mass. All right, 1200 kilogram. Right now, I want to see what happened whether Mr. Barry will survive. Here, die, heavier, lighter, or what else. So Fn is still on the top, so you're going to do m v squared over r minus g. So this time, what are we going to get? We're going to get 1500 Newton, right? So if you do get 1500 Newton, and our Fg is how much? Our Fg is, let's say, 12,000, right? Newton. So feel heavier, lighter, or die? No, Mr. Barry will feel lighter because Fn is less than Fg, so lighter. Lighter. Will he complain? No, not probably not, because this 1500 not close to 0. No. When you have normal force close to 0, then you complain. Then you don't like the sensation that you're experiencing. This is the sensation you're looking for. Otherwise, you would not be going to amusement park and riding the roller coaster. Okay, now that takes us problem number 4. Problem number 4, instead of top, I'm going to put you on the bottom. Because at some time, roller coaster has to be on the bottom, right? Okay, now we need to derive the formula. Remember, the FG is always downward without any exception, and Fn is upward, right? Fn is always upward. If this one go there, if this one go there, then hey, Fn will be because the car is upside down. Get it? All right, so we're gonna start our conversation with Newton's second law. This time is fast because hey, the force, the centripetal force is toward the center. Okay, good. So Fc is equal to mv squared over r. No, that's not how we're gonna do it. We're gonna write all the equations on this side. So what are the equations? So you have Fn minus mg is equal to mac or d squared over r. You have to write anyway. So Fn is equal to mv squared over r plus mg. So if you factor out m, so you get v squared over r plus g. So if you distribute it, so mass is 1200 kilogram. 1200 kilogram. The radius is same, 20 meter, and the velocity is 15. We're gonna keep the velocity same. So mass is 1200. So velocity is 15 means 225. Radius is 20 plus 10, right? So Fn is equal to 1200. This is 20. This is 225 plus 200. All right. So what do we get? We get Fn is equal to 425 over 20 times 1200. So 0 cancel out. This is 60, right? So 60 times 400 is, and 60 times 20 is, and 60 times 5 is 300. All right, so 0.00552. So what is the normal force? So the normal force is 25500 Newton, of course, right? And weight is 12,000 Newton, of course. So now normal force is bigger than weight, of course, but it's just too big, it's more than twice. So you feel not only feel heavier, but too much heavier. You don't want to feel too much heavier, too much lighter. This is the sensation you are not looking for. So you probably want to complain. Anyway, let's move to the next problem, and I'm really getting tired. Next problem is bucket, but we're going to create a moon. But to create a moon, we have to have some understanding, conceptual understanding. We're going to introduce two new concept, frequency, and then the period. When we talk about frequency, we use the lowercase f, and we talk about period with uppercase T. Frequency is cycle over time by definition, and the period is time over cycle. What does cycle mean? It has to do with the circle. If you want to create a circle, just like I did, you have to start at somewhere. So from red to red is one cycle, right? And I made 3 cycles. How do you know I made 3 cycles? You can see it: 1 cycle, 1 cycle, 3 cycles. I made 3 cycles. How many revolutions? 3 revolutions. Okay, good. You get it. So I made 3 revolutions or 3 cycles. They are the same thing. Okay, good. Cycle doesn't have any SI unit, so we put 1, and time has SI unit second. 1 over second is hours. The time SI unit is S. Cycle doesn't have any SI unit, so 1. So S over 1 is just S. So hey, period is just like time. Now again, I want you to get a bucket. So you have a bucket, and then you have a rope, right? And you are rotating, applying some force by your hand, right? By your hand. Okay, so it creates the circular path around on the bucket. Now, what is happening? You make two revolution in 1 second. What does that mean? That just means you making one revolution and two revolution, right? So you do it twice. You make two revolution. That's what it means. Okay. All right. Uh, now, what does that mean in terms of equation? Okay, in terms of equation, you make two cycle in 1 second. However, we're not going to use the frequency. We have to use the time, right? In order to find the velocity, you need the time. So frequency to time is a smooth path if you understand this equation. So now period is equal to the 1/2, right? Because hey, the time is 1, you put 1 over here. I'm going to use the different color. So all right, so the 2 is the time. No, of course not. 2 is the cycle, 1 is the time. 1 is the time. So 1/2. Okay, so 1/2, and don't forget the s. So period is 0.5 second. All right, now what is the next? The next is, of course, you want to try to find the velocity. So velocity is distance over time, but this distance is circular. So don't forget that 2 pi r over t. Always use the big T because it is period. So 2 times 3.14 times a radius, which is 0.6, of course, divided by t is 0.5, and so velocity is 7.5 meter per second. So this is moving with velocity 7.5 meter per second. Now we want to find the centripetal acceleration. How much is the acceleration to the center? Okay, so centripetal acceleration is v squared over r. What does that mean? That means v squared is 7.5 v squared, and r is I don't know, 0.6. So centripetal acceleration is 94 or 95 meter per second squared. This is just too much. So you never want to be sitting in the bucket. No, the most that's why you want to put the water. You don't want to put yourself in the bucket and ask your best friend to rotate it. No, never do that. Put the water, it's safer. If water falls, then the worst thing can happen. You get wet. But water never falls because, hey, you know the velocity. You know the velocity, the minimum velocity. If you give this velocity, the water will never fall. But always give a little bit more so you're safer. You don't get wet. In this cold weather, you get wet, not good. Okay, anyway, so that takes us to the last problem, maybe the moon problem. So moon rotate around the earth. So this is the moon. This is the moon, and this is the earth. Okay, so moon rotates around the earth, right? We know that. Okay, good. Because there is a centripetal force. There is a centripetal force, and that's pulling it to the down, just like roller coaster. Now is the moon. Okay, centripetal force pulling it down. The velocity keep it. So now we need to know what velocity is on the moon. Okay, so how can we find the velocity? Well, we know that it takes, we already kind of know centripetal acceleration, right? Centripetal acceleration, we kind of know that, but we're going to find it again anyway, different way. So it takes 27.3 days for the moon to complete one revolution around the earth. So if that's the case, what happens? So 27.3 day times, of course, you have day, you have hour, times, of course, you have hour, and you have second. So you want to convert it to second. 1 day 24, and 1 hour 3600, right? Hour cancel, day cancel. So you have 27.3 times 24 times 3600, which is only God knows what is it. Maybe 2.4 times 10 raised to 6. Not sure. 10 raised to 6. I don't know. 2.4 times 10 raised to 6. Okay, let me check. 27.3 times 24 times 3600. So tired that my head doesn't work. Oh yeah, I was right. 2.4 times 10 raised to 1, 2, 3, 4, 5. 6 second. Wow, that's pretty good. Okay, so the velocity